Assalamu alaikum and very warm welcome to all of you. Today you're going to learn what is time scaling of signals, what is compression, expansion, how compression and expansion of the signals is done. We'll use visual as well as the mathematical representation for understanding of the time scaling of the signals. So shown here is a original continuous time signal x of t. Do you know why it is continuous time signal? Yes, right. Because the independent variable is time and that is t and it is continuous, so this is called the continuous time signal. So in continuous time we have both the time has the continuous values, similarly the values of the signal, you see these are the continuous values. So you can easily see that original signal exists from -3 up to 3 and it has the maximum amplitude of 1, which is on the when t equals to 0. So let's see graphically how the its compressed version looks like. Time scaling means you scale the signal along this axis. So if you scale it along this axis, whether okay, so we have the two possibility that whether the resulting signal will be compressed as shown here or it will be expanded. Okay, so you can see that original signal exists from -3 up to 3, but the its time scaled version exists from -1.5 up to 1.5, and you see there is no change in the amplitude, so that means the signal is compressed in time. You understand compression and expansion, right? So let's see the next slide. We have the example of expansion. The original signal, again the same signal, so it exists from -3 up to +3, but its expanded signal exists from say -6 up to 6, so that means the signal is expanded by a factor of 2. Now let's do some brief mathematics on it. So mathematically we have a signal x of t and its time scale version is written as y of t, and we say y of t equals to x of at, where a is the scaling factor. So if a is greater than 0, in that case the resulting signal will be compressed, or time compression will happen. And similarly, if a is less than 1 but positive, in that case the signal will be expanded, or we'll have the time expansion. So remember that there's no change in the amplitude during time scaling. Okay, only time axis is change. So let's have a numerical example, and we say we want to scale the signal by a factor of 2. This is along time axis. Okay, so say original signal is y of t, so its expanded form will be its scaled version will be x is equal to 2t, because we are scaling it by a factor of 2. So again, as we did in case of shifting, uh, we'll do the same things here again, and we will replace wherever we have the t by 2t. Okay, because we are using it is scaling, we are scaling it by a factor of 2, so you understand the t can be in the signal equation and it is also in the valid interval, so we will replace in both of the places. Now, so before doing that, let first consider what is our the signal x of t. So the graph I shown you, those, if I write it mathematically, then those graphs are x of t equals to 3 plus t divided by 3 for an interval of 0 to -3 to 0, and x of t equals to 1 minus t by 3 for an interval of 0 to 3. So if you have seen this one, this is the signal forms are triangular waveform. So we have just a pulse of triangular waveform. So This signal, you understand, support is supported in this interval, or you can write that it exists from -3 up to 3, but because the signal equation is different for -3 up to 0 and 0 up to 3, so we write two different equations. Okay, so let's do the mathematics. So the first step is replace t by 2t. So we see we have t here, so we will replace it by 2t. So we have written y of t, which is the scale version of x of t, is equals to 3 plus we have t here, so this t will be replaced by 2t again divided by 3, so it stays the same. Again in the interval we have t, so we replace the t by 2t. So here it is shown uh, that we replace it by 2t. So you see 2 is multiplied here. You can also say bring it here, so it will be divided and also to here, or in other words you can say divide this whole inequality by 2. So if we divide by 2, we get -3 divided by 2, so you get -1.5. 2t divided by 2, you get t, and similarly 3 divided by 1.5, sorry, 3 divided by 2 is 1.5. So we have the resulting valid interval. Okay, so then we have the first part. This is x of t is equal to 3 plus t, so it becomes x of 3 is equal to 3 plus 2t, same divided by 3, and the interval is because divided by 2, so now you have the interval, valid interval, that is -1.5 to 0. So you have -1.5 to 0, so t is equal to or greater than -1.5 and less than or equal to 0. Similarly, for the second part of the signal, that is this one, so again you replace by t by 2t, so you have 1 minus 2t divided by 3, and the interval is because 0 to this, so which we have obtained here, so 0 divided by 2 will result into 0, and 3 divided by 2 will result into 2, and similarly this is 2t, so 2t divided by 2 is t. So for the second segment we have t is equal to or greater than 0 and is less than or equal to 1.5. So in this way the signal becomes compressed. Okay, so that I have shown you in the first figure. Let's move to the next one, and here we have the time expansion scaling factor is 1 by 2. So that's also I have shown you graphically. In this case the signal will expand. So again, the same definition, y of t is the scale time scale version of x of t, and because in general equation we have at, now instead of a we have 1 by 2, so y of t is equal to x of t by 2. So that means we will replace t by 2 in the equation. Okay, so because this signal consists of two equations, so here in the first one we'll replace t by t by 2, and here also t by 2, and also we have two intervals, so for those intervals we also replace t by 2. So original interval is this one, so new interval will be t by 2. So we multiply all the sides by 2, all the terms. Okay, so we get this one will become -3 multiplied by 2 will become -6, then t by 2 multiplied by 2, so 2 cancels, you get t, and similarly 3 multiplied by 6, so you see the interval is expanded. Okay. So we write the final or the scale version signal as y of t equals to 3 plus t by 2. Okay, and it has the interval of -6 to 0. Similarly, y of t equals to 1 minus t by 2, and the interval is this one. So the signal becomes expanded. How do you know this become expanded? Because previously the signal existed from -3 up to 3. Now the signal exists from -6 up to 6. So you understand this is 2 times expanded. So hopefully you understand that, as in the previous lecture of the shifting, uh, we do the replacement of the equation t value in the equation of the signal and also in the interval. So this is equation, here you replace t by whatever value is new. Okay, and also in the interval. So these are quite simple because you have done the similar thing in the previous lecture also. So in this lecture We introduced the time scaling of continuous time signal. We learned how scaling changes the time axis while preserving the amplitude. We studied compression using using x is equal to 2t, that is if you multiply t by 2, so your t by okay t with 2. Okay, so the signal is compressed. Similarly, if we multiply it by 1 by 2, okay, so if we have the resulting signal x y of t is equal to x of t by 2, that means if 1 by 2, that means it will be expanded by the factor of 2. And if we have t replaced by 2t, in that case the resulting signal is compressed by a factor of 2. The focus was on building intuition visually rather than memorization. So hopefully by looking at the figures and then doing the mathematical part, it becomes very easy for you to understand. So in the next lecture, we'll study discrete time signal scaling step by step, both using graphical method and the mathematical representation. So again, you understand this lecture as part of Signal and Systems Foundation course with Python. So in the upcoming videos, we'll also start doing the Python part, that is generating and plotting different signals and performing different operations. So that's all from my side. See you in the next lecture. Goodbye until then.